Okay, now we're going to be talking about domain and range. I don't like this particular example very much because this appears to be an asymptote. I don't know if you're familiar with that word or not, but it's where the function converges towards one value. And as you can see, it looks like it's converging towards x equals 5. And the reason why I don't like this is because in the book, it's showing you that our domain goes from -5 to, it says infinity, and I disagree with that because if this is an asymptote, then it's not going to go, your x values aren't going to go from -5 to infinity, they're going to go to 5. They're not going to reach 5, but they're going to go to 5. So if you can see that, that's great. If you can't see that, hopefully it'll start to make more sense as we get more and more into functions with asymptotes. But that's what it looks like to me, is that this is actually never going to reach 5. It's just going to get closer and closer and closer and closer to 5 as you go towards infinity. So then let's talk about the range. So our range ends here at the upper 5, at y equals 5. So we're including 5 for that. And it goes all the way down to -infinity. So actually, let me rewrite that the other way. There we go. So our range is going from, it's your vertical span, and you can see that span ends right here at y equals 5, and it goes on forever. So it goes y equals -infinity. So we've got that represented here. And then again, let's look at our horizontal. It gets confusing talking about this way because we're looking at horizontal but calling it vertical, and then looking at vertical and calling it horizontal. But let's look at our values, our x values. So our x values go from -5, which is what we showed here, and they go to positive, towards +5, but not including +5. So that's what I was talking about in this one. Your book says that it goes to infinity, which I don't agree with because it doesn't quite take on this type of a motion. It takes on more of an asymptote kind of motion. So you use whichever way you want to, and hopefully it'll make more sense later. And here's another example. Let's do the domain and range for this one. So our domain, I always get these confused, and the best thing I can think of, if I were to say, this is my domain, I would say that while opening my hands out this way. As sad as it is, that's the only way I can keep them straight. So domain is our span of x values. So there's my span of x values in here, and it's not inclusive of 3. So I'm going to say it's from, my domain is from -3 to inclusive of 1. So it's going to look like that. And then my range is my, my vertical distance. So those are my y values. So I'm going from y equals -4, and that's inclusive. Whoops. -4, and that's going up to 0. And that is inclusive because it hits right here. So we're going to include 0. And then let's see. The domain and range of this one. Our domain is going to be our span of x values, and that's not including -3. And it goes to 1, and that is including 1. And then our range goes from -infinity to, oh, sorry, it's not going to -infinity. It stops there. I have some distractions in the background. Sorry about that, guys. So it's going to -4, and it is inclusive, and that's going up to 0. And I'm just realizing that that's actually the 0 here is open, so it's not going to hit. And this one, it looks like it just gets to 0 and goes back down again. So it doesn't actually overlap the 0 there either. So let's leave that in open parenthesis. And here's another example where we just have the graph. So in this one, what is the domain? So the domain is our horizontal span. So we're going from, it looks like 1975, 1974 maybe. Oops, sorry, I keep doing that. It's going from 1974. Oh, and this one we're just doing an inequality. Sorry, we're doing this one. We're doing our inequality notation. So our domain is ranging from x values greater than or equal to 73, and then less than or equal to, let's say, what's that, about 2010. And then our range, so that's how much we're, our vertical distance is. We're going from here, which let's say that's about 180. So our range is going to be values from 180 to, it looks like 2000. So there are your domain and range, still using interval notation. And then in this one, in inequality notation for the last slide, and then interval notation for this one. So let's look, we've got 1950 and ending at 2000. So our range is going to be inclusive of 1950 to 2000. And our domain, I just did that backwards. See, I told you I always confuse these. And again, I'm a little distracted. I've got some kids hollering in the background. It's a little distracting too. So there you go. So our domain is our horizontal distance, and that's going from 1950 to 2000. And then our range is our vertical distance, and that's going from what looks like, I don't know, about 47. So we're going to include 47 to, looks like it caps out at about 90. So this is definitely a matter of perspective. So if you have open brackets, that's all your interpretation on this particular one. It's a lot harder when we're looking at the graph and we're coming up with these versus whether or not we have an actual function or an equation that we can confirm our values with. So this next section, I'll probably skip. I'll let you look at this by yourselves. I'll just do a quick run through. So these are called toolkit functions. So every function, you kind of have your base function, and then you can change that depending on transformations and your shifts of that function. So in this particular one, it's called the constant function. And this is showing you what the domain would be for a constant function and what the range would be. Because this is a constant function of the form f of x equals c, then our range is just going to go from c to c. If we had a constant function that was, it wouldn't be a function. That's why we're not talking about this, so never mind that. So in this case, it's just your horizontal value at f of x equals c. And then here's another example. This is called the identity function because it's your x equals your y, or your f of x equals your x value. So it's going to be when, let's say when 1 is 1, the function is 1. When x is 2, the function is 2. That kind of thing. So it's just identity. It's the same thing. Here's your absolute value. So for any x value that you put in, you're going to keep it a positive function value. Here is your typical quadratic function. And again, we start to, this should be squared up here. We start to shift things when we do something like x minus 1 squared plus 3. This starts to shift this around, but it still kind of sticks to the same domain. The domain and range change based on where it is in that graph, in that Cartesian coordinate system. So here's the cubic function. That's what that typically looks like. And again, these can go wider, they can move, they can go like this. It all depends on what those extra numbers are in that equation. But the toolkit function, the basic function, is going to have these domain and ranges. So same thing, here's your reciprocal toolkit function and your reciprocal squared, your square root function, your cube root function. And now here, this one, I believe we're being asked to, find the domain and range of this one. So our domain is going to be including -4 to infinity. So you can see it's got the arrow indicating that it goes on forever. And then our range is going to be from 0, and it's inclusive. I've muddled it up now, but it's including that point on the number line. So it's going to go from 0, 0 to infinity, because that keeps going up. So that's going to be our range for this one, domain and range for that one. Let me just double check this one. Okay, now we're going to be getting into piecewise functions. I think I'm going to take a break. Oh no, this is actually pretty short. Let me just finish this off then. So now you can see that something different happens when x equals 10. This is what's called a piecewise function. So you have one function that tells you what to do from here, and then you have another function that's telling you what to do from here. So typically these are written in a different way. So this one could say, I'm going to fudge this up completely, but we've got c of n equals something when x is greater than 0 but less than 10, and then we've got something else from when x is greater than or equal to 10. So that's an example of what this might look like, this function notation might look like. Here's another example. You can see something is happening, something different is happening when x equals 2. And in this case, here it's showing our 3 different scenarios. So we've got f of x equals x squared when x is less than or equal to 1. So it's showing you this part. This one is saying that the function equals 3 when x is between 2 and 1. So here you can see we've got our x equals 3. And then the last part is saying that our function equals x if x is greater than 2. So that's the identity function. And that only happens when x is greater than 2. So here we've got that part. Now we can put them all together, and it's going to make up this. So sometimes the pieces connect, as in this example and this example, and sometimes they don't. Sometimes they're completely separated. So this is an example of 2 different types of piecewise functions. And I believe, now we're on to the next section, so I'll cover that in another video.